So once again, I will repeat. I am trying to write the code in MATLAB to solve our nonlinear unconstrained optimization problem, that is minimize f of x comma y that's equal to 5x square plus 6y square plus 10, right? So in a MATLAB, generally I'm start with the CLC and clear all commands. Now I am initializing I want to initialize the both decision variables x and y. Randomly I have to initialize the both decision variables x and y. If you want to random initialize the decision variables x and y, you have to give some boundaries. In what range you want to give? In between what range you want to randomly initialize the x and y values? I want to initialize the x and y values in the range between the -10 to +10. I am considering, you can consider any value between. Okay. So here I consider the -10 and +10. Later, I want to randomly initialize the x value and I want to randomly initialize the y value. So this is the piece of code we are using. Yesterday also I explained, right? Rand is nothing but a function which generates the value between the 0 and 1. Between 0 and 1. Suppose the rand function give the value 0, then what happened? Your x value will be lower value. That means -10. If the rand value equal to 1, then what happened? Low plus up minus low. Low will be cancelled with up. That means x equal to up, x equal to 10. So like that, from a -10 to +10, you can random initialize some value and assign that value to the variable x. Random initialization of the variable x. Similarly, this is the random initialization of the variable y. After random initialization, we have to initialize the learning rate eta, and also we need to initialize the number of epochs also. We need to initialize the number of epochs also. So what next step? So in the gradient descent algorithm, we need to calculate the step 2, step 3, and step 4. Yesterday we discussed the second step, third step, and fourth step. What is the second step? So second step is the gradient calculation. Third step is the step length calculation. Fourth step is the variable updation. So these three steps will be repeated. Now gradient calculation, right? So you have to calculate the gradient. Okay. So gradient, but here we have the two variables. Previously we had the only one variable, one gradient. Here we have the two variables. We need to calculate the two gradients. That means dou f by dou x and dou f by dou y. So we, in front of you, there is an object function, right? So what is the dou f by dou x? Dou f by dou x equal to 10 into x and dou f by dou y equal to 12 into y. You can see I have a function f equal to 5x square plus 6y square plus 10. So what is the dou f by dou x? That is the 10 into x, and dou f by dou y, that's equal to 12 into y. So now we need to calculate those gradients. So gradient x equal to what is the gradient x? That is the 10 multiplied by x, and the gradient y, that's equal to 12 multiplied by y, right? Dou f by dou x and dou f by dou y values I'm writing, just that's it. So what next? Once we calculate the gradient, we need to calculate the step length for each variable. So each variable means delta x, that means change in length for a variable x, equal to how we calculate the delta x value. So delta x value equal to minus eta multiplied by, we discussed yesterday, that's why I'm not going explaining again. How we calculate the step length? That's the minus eta into gradient, minus eta into dou f by dou x. So delta x equal to minus eta into dou f by dou x, nothing but the gradient x. And what else we need to calculate? Del y also. Change in step length for the variable y. So del y equal to again minus eta multiplied by, so gradient x. Is it right, or we need to change anything? Here, what change you have to intentionally, I mean incorporating by mistake here. So it is the gradient y, not x, because if you want to calculate the step length of the y, you have to calculate the gradient of the y. Okay. Now, after calculating the delta x, change in x value, change in y value. So what we are going to calculate next? We are going to update the variables. So update the variable means x equal to x plus delta x, and similarly y equal to y plus delta y. Okay. So this is the gradient calculation, and this is the step length calculation, and this is the updation. These 3 steps should be repeated, right? So what we can do, I have to keep all these 6 steps in a iterative loop. So what is our iterative loop? For iter equal to 1 to epochs, max the number of iterations we initialize regular epochs. Okay, and you have to close this for loop end. So if you want, you can maintain some small tab also. You can maintain small tab also. Okay. Now, if you want to print the value of final values of x and y, you can write fprintf. Okay. So that's equal to, so x value equal to percentage 0.2f up to 2 decimals 0.2f, and comma y value equal to percentage 0.2f, comma the values are our decision variables in our problem. Decision variables in our problem are x and y. For x and y, x comma y. So that's it. That's how we can write the code to solve the non-linear 2 variable or multi-variable. If one more variable, one more gradient, one more step length, one more updation, right? If the number of variables are increases, definitely your calculations are increases. The number of gradient calculation increases, number of step length calculation increases, and number of updation of the values also increases. Okay. So just you can run this code. So you can see it is giving the solution as x equal to 0, y equal to 0. Of course, we know, right? So at what value of x and y, this function will be have the minimum value. Even the x value, y values are negative whole square, it will become a larger value. It will not minimum. So the function will be minimum at x equal to 0 and y equal to 0. So we are getting the same thing, x equal to 0, y equal to 0. So because I am choosing the very small examples, because we have to understand the flow of code. And we have to know whether the solution is right or wrong. Because we know the solution, we know the correct answer for this problem. So I am verifying it, x equal to 0 and y equal to 0. I am also getting the same thing using the gradient descent algorithm. So this is how we are using the MATLAB. It is the MATLAB code to solve the 2 variable or multivariable nonlinear unconstrained optimization problem using MATLAB. Nonlinear optimization problem using MATLAB. Okay. Just I want to share this code. So I will give some assignments so you can try to write a code in the MATLAB to solve those assignment problems. So that is your for practice only. So try to write the MATLAB code to solve the here I will. Yeah, this is the code I am sharing with you to write a MATLAB code to solve the nonlinear optimization problem using the gradient descent algorithm. So I think you are clear with the coding part of this one. Okay. Next, I am trying to write the code in the Python also. I'm trying to write the code in the Python also. Okay. So what we will do, go to Visual Studio. Okay. And file, open folder. So here I want to create a folder called a class folder. Just I'm giving my name, some name class folder. In this folder, I want to write the code. And open the new file, gda two variables dot py. Py extension I am writing. Okay. Py extension I am writing. Where it is? So new file. Some file name dot py extension. Okay. Just save this file. Now it's open. Okay. Now we will try to write the code to solve this problem. So anyone, please tell me what we have to do. First, we have to import NumPy library, NumPy by NumPy as NP, and also import math library as empty, and also import random to generate the random number. Right? So what we have to do now? In the Python, I am writing the code now. So what we have to do now? Next. Yeah, as usual, same steps. So initialization of x and y, because I have the two variables, f of xy equal to 5x square plus 6y square plus 10. Right? So what are the variables? We have the x and y. We have the variables x and y. We have the variables x and y, right? So we have to randomly initialize the x and y. So x equal to random random dot uniform. From the uniform distribution, randomly generate the some value between -10 to +10, and that value will be assigned to the variable called x. That is the initial value of the x. That is the initial value of the x. That is the initial value of the x, right? Next. And similarly, we have to randomly state the y value, y equal to random dot uniform in the range of -10 to +10. You can choose any value for that range. So here in semicolons are not required in case of the Python, but in case of the MATLAB, it's better to use the semicolon at end of the every line. So x and y values are randomly initialized. So what next? We need to initialize the value of eta, that's the learning rate, and we need to initialize the number of epochs. So number of epochs. So we can take some number of epochs that's equal to 1000 like this, some. So the initialization is completed. So what next our steps? Same. What we are doing earlier, same thing. One is the gradient of x. Gradient x. What is the gradient x? Our function is f of x comma y equal to 5x square plus 6y square. So what is the dou f by dou x? That is the 10 multiplied by x. Right? And whatever the gradient y function is, our function is, I want to show that function.
2.
This is the function f of x comma y equal to 5x square plus 6y square plus 10. So what is the dou f by dou y? So dou f by dou y equal to 12 into y.
12y, yeah.
So dou f by dou y, that's equal to dou f by dou y, that's equal to 12 multiplied by y. Sorry. These semicolons are not required in case of the Python. So once you calculate the gradients, next thing is delta x calculation. So delta x equal to minus eta multiplied by gradient of x. And del y is equal to minus eta of gradient y. Okay. So del y del x calculated. Later, what the next step? We are going to update the x and y values.
X and y.
So x equal to x plus delta x and y equal to y plus delta y. That's it. So this is the gradient calculation, and this is the delta x delta, that means change in step length calculation, and last two parameters are the updation of the variables. Right? So, and these all the things should be repeated. All the things should be repeated. So repeated means we have to keep everything in the for loop. So for iter in range. Iter in range of how many epochs? What we defined earlier, epochs we have to pass and terminate with the semicolon. That's it. Right? So this is how we can write. So finally, I want to print x and y values. So print. So x equal to percentage 0.2f and y equal to percentage 0.2f, x and y values. That is the x comma y. So I want to print the value. That's it. So simply you can run this cell. So you got the x and y values are 0 and 0. In the MATLAB also we are getting 0 and 0, and here also we are getting the values as 0 and 0. Because we know the solution, that function will be minimum at x equal to 0 and y equal to 0. Okay, so this is how we can write the code using Python to calculate the to find the optimal solution of a nonlinear unconstrained optimization problem using the gradient descent algorithm. You no need to follow the same logic, but different people will follow the different approach. Different people will apply the different logic to write a programming. Just what logic I have, I am showing in front of you. So, but the thought is same. The idea will be same. That is, you need to calculate the gradient, you need to calculate the change in step length, and you need to update the variable. These are the 3 steps you have to do. Whether you want to use the for loop or you want to use the while loop, whatever process you want to follow, what code you want to write, that is based on your choice. So this is how we are using the Python code to find the gradient descent algorithm. So here the Python code I have written in my Visual Studio Code, so which is installed in my local machine. Suppose if that is not available in the local machine, then what we can do? So you may go to the Google Colab. If not available, then you can go to the Google Colab. So Google Colab I told yesterday, right? So Google Colab is a cloud platform. Google Colab is a cloud platform to run the Python script. So just if you have the Gmail account, that is sufficient to run the Python script. Okay. So how we will do this?
Can I ask a question?
Madam, please.
Yeah. Actually, this functions that we use, like in the earlier problem, you had given linprog.
Madam.
Linprog was a function given. So that is in which library? How do we import it?
Hello. It is from the SciPy, madam. SCYPY. In Python or in MATLAB?
Actually, I used Google Colab. So that is
which, madam?
MATLAB, I think. Yeah.
MATLAB, huh?
Yeah.
In MATLAB, we can directly use linprog, madam. Yesterday we discussed it, right?
Yeah, all those parameters I had given. I got some error. I'll send it. I'll take it separately if you think it's.
Just you can you can send
yeah, I have mailed
WhatsApp,
actually,
madam, personally.
you. Yeah, I have mailed the link where I have
let you know where the
program.
mistake is actually.
Yeah. Okay.
So now I'm trying to write the same Python code in the Google Colab. So Google Colab is a cloud platform. So Google Colab, and it will ask the Gmail account. So actually I was logged with my Gmail account, so it's not asking any credentials. Directly click on the new notebook. So that's your choice. Whether you want to open the existing notebook or if you want to create a new notebook, that is your choice. Just I am creating the new notebook. Okay. So in this notebook, you can see a small cell with arrow mark, right? So in this cell, we can write the code. In this cell, we can write the code. So it's a Python code only. But the thing is, we are doing it in the cloud. So cloud means it will be stored in the Google Cloud only. So whenever you want, you can retrieve the same code and you can execute whenever you want, but internet is required. That's it. Okay, now I want to write the same code what I have written in my system that can be applicable here. So what the code here? Import numpy as np and import libraries. Import math as mt and import random for the random value generation, random value initialization. So run this one. If you click on that white arrow mark, the script which is written within that cell will be executed. It will be run. Done. So after importing all the required libraries, next I want to open one more cell, code cell. So click on this plus code, or you can click here plus code, and one more cell will be come into picture. Now you can write whatever the code is remaining. What next we have to do? We are going for the initialization. Next step is initialization, right? So or you can write where it is, write a text. So this is called as importing library. So this is the importing library, like a comment you can keep, and you can move it to the upside. Now importing library is completed. What next? What we are going to do? Initialization. So in the initialization, what we have to do? We have to initialize all our variables. We need to initialize all our variables, and we need to initialize the learning rate, and we need to initialize the maximum number of epochs you want to run this algorithm. So what is those things? X equal to, I want randomly initialize the X value. Our decision variable X value, that is the X equal to random dot uniform. So in the range of, it's your choice. I am taking the -10, 10. It's your choice. And Y equal to random dot uniform, the range of -10, 10. And X and Y values initialization is completed. What next we have to do? Eta value, that's equal to 0.1, and epochs, maximum number of iterations, that's equal to 1000, like that I have considered. Again, run this cell. So you can write complete code in a single cell, or you can write the code in different blocks also. It is called a Jupyter Notebook. In the Jupyter Notebook, these are called as the cells. So you can write the complete code in a single cell. Okay. Or you can write a small pieces of a code in a different cells also. You can write and execute. So what this? So after that, what we have to do? So we have to write the for loop and gradient calculations. So for iter in range of epochs. That means whatever the number of epochs we define, those number of iterations loop will be repeated. Now we have to calculate the gradient of x. What is the gradient of x? As the 5x square. That means 10 into x
10x.
gradient. And what about the gradient y? Gradient y equal to 6y square. 6y square means it is the 12 into y gradient. So once we calculate the gradients, what next we have to calculate? Change in variables.
Yeah.
Step length. So step length equal to, how we calculate step length? That is the minus eta. Yesterday we discussed all the things. Minus eta multiplied by dou f by dou x. That is the gradient of x. Similarly, how we calculate the change in step length for the variable y? Del y equal to minus eta minus, sorry. So minus eta multiplied by gradient y. Sorry, gradient y. So delta x, delta y is calculated. What next we have to do? We need to update the variable. How we update the variable? X equal to x plus delta x, y equal to y plus delta y. That's it. So this process will be repeated until we reach the maximum number of epochs what we define. And later, I want to print the optimal solution. So print. So you can write what you want inside the quotes. So optimal, your choice, what you want to print, you can write like that, optimal solution. X equal to percentage 0.2f and y equal to percentage 0.2 f and x comma y. That's it. So run this algorithm first in cell. Once it is over, now come to the printing section. Now it's showing the 0 and 0. So actually 0 and 0. So I'm getting the values are 0 and 0 values. X and y values are 0 and 0. So whatever, whether it's a Python, whether it's a MATLAB, whether you are using the Visual Studio Code, whether you are using the Google Cloud, so whatever you take in the platform, but the ultimate solution will be same. So hope you understand this complete Python script and MATLAB script for writing a code to solve the nonlinear unconstant optimization with the multivariables using the gradient descent algorithm. Okay, so if you want, I will share this Jupyter file also. So you can maybe some people facing an issue to access my collab node. I will do one thing. I will share. I don't want to give any restriction. Anyone with this link, copy link, and done. And I want to share. So I think just a minute. Just give me 1 minute time, please. Okay. So hope you understand the multivariable gradient descent algorithm and its implementation using the MATLAB and also using Python. And now we are moving to a new topic, how we incorporate, how we use this optimization for a machine learning. So what is the need of this optimization? Why you are studying, how it will be useful in a machine learning process? While machine learning model, during the process of training process of a machine learning model, how this optimization algorithm will help. That I am trying to explain for today and for the next 3 days also, but different types of gradient descent algorithm variants. Different types of gradient descent algorithm variants. Okay. Okay. So in order to explain the process or utilization of the optimization technique, for a machine learning, I'm taking a very, very small machine learning model, basic machine learning model that is called as the simple linear regression model. So just I'm trying to explain, first I'm trying to explain simple linear regression model. Simple linear regression model. Okay, done. So first of all, actually, mainly in a real time, there are the two types of problems. One is called as the regression problem, and another is called as the classification problem. I don't want to go in depth about this part. Just I'm giving the overview. Classification problem. I'm trying to so general in the real time, there are the two types of problems will exist. One is called as the regression problem and the classification problem. So regression problem means the variable what you are going to predict. The variable what you are going to predict is a continuous number. In a problem, the problem what you are attempting, in that problem, you have one variable going to predict. And that variable is a continuous in nature. So such type of problems are called as the regression problem. Examples are like estimation of the temperature. Your temperature may be a 35 degree, 36 degree, 40 degree, 42 degree, 43 degree. any temperature, it is a continuous number, 43.5 or 40.5. So like that, any number can be come into picture while prediction. So that comes under the regression problem. Whereas coming to the classification problem means, again in the classification problem, we have the two types of problems. One is called as the binary classification problem, another is the categorical classification problem. Binary classification problem and categorical classification problem. Okay. So what is the classification problem? In the classification problem, the variable what we are going to predict, the variable what we are going to estimate, that variable is not a continuous, but it is a discrete. But it is a discrete value. So that is called as the classification problem. Example, let's assume you are working on a problem called COVID diagnosis, COVID prediction. Let's assume you are working on a problem called COVID prediction. So what is your outcome? What is your out variable? Whether he has a COVID positive or negative. COVID positive or negative, that's it, either 0 or 1. This is a discrete value. Your variable has only two options, either 0 or 1. So that comes under the binary classification problem. You have the two discrete values, either 0 or 1. So it is called as the binary classification problem. Or let's assume you are developing an application. That application will help to identify the type of Indian currency note. Let's assume you are developing an application, a mobile application. That mobile application will tell what is the Indian currency note we kept in denomination of the Indian currency note that we kept in front of the camera. In front of the camera. Okay. So like if you give the 10 rupee note, it will tell it is the 10 rupee. If you give the 20 rupee note, it will tell it is the 20 rupee. That means we have the multiple classes, 10 rupee, 20 rupee, like that. So that type of discrete classes, 10 rupee class, 20 rupee class, 50 rupee class, discrete classes we have. So that comes under the categorical classification problem. This is the categorical classification problem, and this is the binary classification problem. So this is the different, generally the real time, most of the real time problems either comes under the regression problem or it comes under the classification problem. Now, if you want to solve this type of regression problem, so one of the model, machine learning model that is available is called as the simple linear regression model. So simple linear regression model is used to solve the regression problems. Simple linear regression model is used to solve the regression problems. Used to solve the regression problems. Okay, clear, right? I hope you understand. Done. So now coming to the what is the simple linear regression model? Generally, simple linear regression model is used in a scenarios where we are going to estimate a output variable based on the single input variable. Simple linear regression model is a model, is a machine learning model which is able to predict a single variable, single output variable based on the single input feature or the single input variable. So that means that model will expect one input and it will give the one output. In such scenario, we are using the simple linear regression model. Right, please. So let's assume, let case that I'm giving, let's assume I am trying to forecast the load at a particular time on a substation. Let's assume I am trying to forecast a load at a particular time on a substation. Based on the load available at the same time, but yesterday, previous day. That means 24 hours back. So L of t minus 24. Right? That means I am trying to forecast the load L of t at load at a particular time based on the load is available in the last 2 hours, before 24 hours back. That means one day before. Example is, let us do now it is a 2:20, right? I am want to predict a load at 3 p.m. today based on the load available at 3 p.m. yesterday, 24 hours back. So if you are using such type of cases, so then we can go with the simple linear regression model because there is only one input. Based on this input, I am trying to predict the output variable. Based on this input, I am going to predict the output variable. Single input and single output. So such type of problems can be attempted by using the simple linear regression model. So that's the only facility for the simple linear regression model. It will expect one input and it will give the one output. I think it's clear. So in what scenarios, in which scenarios we can use the simple linear regression model, right? Now, so before going to the simple linear regression model, for any machine learning model, if you want to train, if you want to make any machine learning model, so what is required? If we have a child, okay, so let us assume, so there is a simple linear regression model. There is a simple linear regression model which is able to predict one output, let us assume L of t, based on the one input L of t minus 24. That means I want to build one simple linear regression model, to predict an output variable L of t based on the load available at 24 hours before, right? So see, this means the machine learning model is available, right? So if only machine learning model is available, what else required for us? To make that model to learn something, what are required? What are the things are required? The data is required, right? So let's prepare a data. Let's assume, just I'm giving some example, that maybe if the x1 is the input and the output is the y1, x2 is the input, the output is the y2, x3 is the input and output is the y3, x4 is the input and y4 is the output. So you have the historical data. So that means we have to prepare the data. Historical data you have to prepare. For example, how you prepare the historical data? So if my output variable is the load at 2 p.m. today, this is already available. So you have to feed the data here. And what is the input? Yesterday. So yesterday 2 p.m. load. And if the output is a 1 p.m. load, then this is the yesterday's 1 p.m. load. And here it is a 1 p.m. load. Sorry, it is a 12 p.m. load available. Then this will going to predict based on the yesterday 12 p.m. load, right? So like that, we have to prepare the data. Like this, we have to prepare the data. So let's assume all these data samples are available. Let's assume x1, y1, x2, y2, x3, y3, x4, y4, all these data are available. So you have to feed this data to this simple linear regression model and apply the learning algorithm, any optimization technique, so that this model parameters of this simple linear regression model will be updated and it will learn accordingly. Okay. Now I'm trying to explain in detail about the simple linear regression model. So let's assume. So this is my input X, like L of t minus 24. And based on this input, I'm going to, my output will be Y. That is the output. Output will be Y and this will be the X. So actually what the simple linear regression model will do is, let's assume the data points are, my historical data points are maybe like what 1 and 2. So just taking some random values like 2 and 3 and 3 and 5 and 1 and 4, like this, let us do. So let's consider multiple data points. Multiple data points are there, right? Now what this simple linear regression model will do is, it will try to develop a line. Which has the minimum distance. It has the minimum distance from all these data points. So that means, suppose if you consider a line here, then it has the distance from here to here. This is the distance from this point to this point. This is the distance, and from this point to this point, this is the distance, like this. So it's not an optimal line. It's not a minimum distance line. So it will try to identify a minimum distance such that it has the minimum distance from all these data points. Like this. Clear, right? Okay, done. So otherwise, I will explain once again. The simple linear regression model is nothing but it is trying to build a straight line which is passing through most of the data points and which has the minimum distance from all the historical data points. All the historical data points. So I'm trying to explain once again all this stuff here. Let's assume I have a input x1 and corresponding output is y1. Let's assume this is the data point. Okay. And I have the input x2 and the corresponding output is y2 and the corresponding output is y2. Let's assume. So this is the corresponding output y2. So this is the input x1. This is the x1 comma y1 and this is the x2 comma y2. x1 comma y1 and x2 comma y2. Okay. Now, so what it will do, simple regression model do is it will try to get a line. It will try to get a line which has a minimum distance from these two data points. So it will not pass through this data point. If it is passed through this data point, it is far away from this point. It is not passing to this data point. If the line is passing to this data point, then it is far away from the first point. So that means it will try to satisfy both. It's not far away from the either one or two. It try to get the minimum distance. In trying to get the minimum distance from all the points. So from here, okay. From here, so see, for this x1 input, and the point on the line is called as the predicted value. That's called as the predicted value from the simple linear regression model for this input x1. And for this x2, the point on the line, so this is called as the predicted value for the second sample. Predicted value for the second sample. That means for this input, my machine learning model is this is the predicting and actual value this one. So this is called as the error. And for this input, my machine learning model is predicting this point, and whereas my actual point is this one, and this is called as the error. And this is difference is called as error, and this difference is called as the error. So while training your machine learning model, it's trying to update the parameters in such a way that its total error should be minimum. This total error should be minimum. Like that, the machine learning model parameters will be updated. And I want to tell one more thing. The simple linear regression model will try to give a linear relation between your output variable and your input variable. Output variable and your input variable. Linear relation, line equation. It will give a line equation. So see, every machine learning model, what the machine learning model is. So back end of the every machine model, some equations, some mathematical equations, which trying to build some relation, some approximate relation between the output variables and the input variables. So don't confuse much about the machine learning model. So machine learning model is nothing but some mathematical relation. It's trying to build some approximate mathematical relation between the output and input. Don't expect exact mathematical relation. If it is an exact mathematical relation, we can go for the deterministic approach only. It will try to get the most approximate relation between the input variable and output variable where there is no proper relation is available between the two variables. We are trying to build a machine learning model to predict some output variable based on the input variable where there is no proper relation is available. Then what these machine learning algorithms and models will do, it try to build some approximate relation, mathematical relation between your output variable and the input variable, some mathematical relation. So it's not in real time, it is a highly non-linear relation. Simple linear regression model is a very limited power. I'm trying to build a linear relation, but in the real time, the output variable and input variables are very highly non-linear. Then you may ask, then why you choose this one? Because we are in the basic FDP, and here we are motto is trying to understand how optimization is useful in machine learning training perspective. That's why I consider a very small machine learning model that is called a simple linear regression model. Okay, so now I'm trying to I think you are clear with the simple linear regression model. The simple linear regression model is nothing but they try to develop a straight line which is minimum distance or minimum error from the actual data points. Okay. Now I will explain in detail further. So please, so let's assume this is my simple linear regression model and it taking one input that is called X and it will take one output that is called Y. Right? Now, what I tell, so this simple linear regression model will give a linear equation which will provide the relation between your output value and your input value, linear relation. And what output value coming from the model, that is called as a predicted value. What output value coming from the model, that is called as a predicted value. What available in the data set for this input X, what is the output Y, that is called as the actual value. Right? So I have, see, let us zoom. I want to forecast the load on a substation. Then I go to some Alexa substation. I take all the previous hours load data and I prepare the data like this. So X1 and Y1 load. And for input X2, actual value of the output is Y2A. For input X3, actual value of the load equal to Y3A. And for input X4, actual value equal to Y4A. Like this, we have to prepare the data. Right? Now, if you feed this input X1 to this machine learning model, whatever the output is coming from the machine learning model, that is called as a predicted value. That is called as a predicted value. And whereas this one is called as the actual value for that input. And the difference between this actual value and this predicted value should be as minimum as possible. The difference between the actual value and predicted value should be as minimum as possible. And I said earlier, that is, for X, for a Y, YP, so your simple linear regression model will give the linear relation. Try to get a line, a straight line, which has the minimum distance from all the data points, right? So that means, let us assume, so this is the one data point and this is the one data point like this. And let us assume this is the line which has the minimum distance from all the data points. And how we represent this line? How we represent this line? How we represent this line? So we can represent this line as a linear equation, line equation. That is M into input X plus Y intercept C. Right? That means your predicted output is depending upon the point on the line. The predicted value is nothing but the points on the line. For this X1, so the point on the line is the predicted value and this is called as the actual value. For let us do for X2, point on the line is the predicted value and this value is called as the actual value. Right? So hope you understand the points on the line are called as the predicted value, YPs, because and the data points are called as the actual output values for the given inputs. Now, how we represent the mathematical model of a simple linear regression model backend? So YP predicted value equal to M into X input. So this is the X, right? So into M into X, M into X, and we have to add a bias parameter or a constant C. So now we have YP equal to YP, predicted value YP equal to M into X plus C. So YP equal to M into X plus C. This is the what your model is predicting. This is what your model is predicting. So for this input X1, if you are giving the input X1, so then predicted value from the machine learning model equal to M into your input value X1 plus your bias value C. That is your predicted value. And whereas this part is called as your actual value. This is your predicted value and this is called as actual value. This difference should be minimum. The error should be minimum. The error should be minimum. Right? And similarly, suppose if you are feeding the X2, then whatever the prediction, the prediction y2p equal to m into x2 plus c. Similarly, if you pass the x3, then your prediction will be prediction from your machine learning model equal to m into x3 plus c. Right? So this is all how we are going to predict from your simple linear regression model y1p, y2p, and y3p, and like that. And whereas this y1a, y2a, y3a are the corresponding actual values. Corresponding actual values. Now, what is our motto? What is the main motto of learning process? During the learning process,
Sorry,
the
sir.
model parameters will...
Sorry for the disturbance, sir.
Madam, sir, please, sir.
Screen is not visible, sir.
Ayyo. Sorry, sir. Okay. Sorry. Now is it okay, sir?
Yes, now it is okay.
Okay.
In so many minutes, it was not visible.
Okay. Then I will once again explain, sir, please.
Okay, sir.
Now you're able to see the screen, right?
Yes.
Thank you,
okay.
sir. Otherwise, what I'm saying, that will be wasted otherwise. So thank you. So once again, I'm trying to explain about the simple linear regression model. The simple linear regression model will try to predict only one variable y based on the some input variable x. So one input and one output. That's it. I'm taking a very small model. Okay. One input, one output, x. Like, for example, let's assume I have the two parameters, one input parameter and one output parameter, x and y. That may be anything. As I said earlier, I'm trying to forecast the load at a particular time t based on the load at 24 hours before. I'm trying to forecast the load at 3 p.m. today based on the load available yesterday 3 p.m. That's my input, and I'm going to predict next 3 p.m. That is my output. So one output and one input. So if you want to work on machine learning, we have to prepare the data. We need some data. So we have to prepare some data. Let's assume x1 and this is the y1 actual value. For the x2, actual value is y2a. And for x3, actual value is y3a. For x4, actual value is y4a. Like that, I have the different samples. Here I consider only 4 samples, but we are using the thousands of samples, hundreds of samples while training the machine learning model. Let's tell you these are the samples are available. Okay. Now I'm trying to draw the plots, small plot, to represent all these data points. Let's assume this is the x1 and this is the x2 and this is the x3 and this is the, let's assume, x4. So for x1, corresponding output equal to, let's assume, y1a. For x2, corresponding output equal to y2a. For x3, corresponding output equal to y3a. For x4, corresponding output equal to y4a. So this is the representation of the data points on the space, two-dimensional space. Okay. Now, what the simple linear regression model will do is, it trying to build a linear relation between your output variable and your input variable. A linear relation between the output variable and the input variable. So linear relation is a line. So it is trying to identify a line. It is trying to identify a line which has a minimum distance from all these data points. Minimum distance from all these data points. Okay. So let us do for the x1, whatever the point on the, for a corresponding x1, the point on this line will represent the predictions. So y1p. This is the predicted value, and this is called as your error. for that sample. For the second sample, if the input is x2, my actual predicted output is on the line, that is called y2p, but actual value from the data set is a y2a, and this is called as the error. Similarly, for x3, if the point on that line will give the predicted value, and this is called as the actual value. This is called as the error. So why during the learning process, during the training process, the model parameters of the simple linear regression model will be updated in such a way that the line will be close to the most of the data points. Then this error will be minimum. Total error will be minimum. Like that, the model parameters will be updated and line will be updated. And still, I am telling one more small example. Same thing. Initially, we are randomly initialize some line like this. Now pass the first data point. My first data point is somewhere here, right? Then my model parameters will be updated such that this line will be coming closer to my data point. Now, when I'm passing the second sample, my second sample is somewhere here. Then what it will do? Now, because one line is here, one point is here, one point is here. Now, my model parameter will be updated such that my line will be somewhere closer to the both two. Not close to that one, not close to this one. Such that total error will be minimum. Like that, it will be updated. Right? Suppose my third point is y3a somewhere here. Then what happened? My model parameters will be updated such that it will be further closer. Because here errorless, here somewhat more. If it is moving in upward direction, it is far away from these two data points, then error will be increases. Okay, like that, my model parameter will be updated, my line will be shifted, and finally at end of the algorithm, it will stop some point like this. And what are the points on that line? All the points will represent the predicted values from this model, and the remaining red points are called as the actual values. Right? So from this analysis, what this simple linear regression model is trying to do, it is trying to establish a linear relation between your output variable and your input variable, input feature. Linear relation, because it will give a line equation. It will give an approximate line equation which is closest to the most of the data points, so that net error will be minimum. So main goal of learning algorithm for this application, for this simple regression model, any learning algorithm, main goal is it trying to update the model parameters of the simple linear regression model such that my line will be updated, and finally it will have the minimum distance from all the data points, total minimum distance from all the data points. That's called total error will be minimum, right? So finally, it will try to build a linear relation between your output value and your input value. So how we represent this line? Linear equation, how we represent this line? We know that we can represent this line as a y equal to mx plus c, right? That means your predicted value, because the points on the line will represent the predictions, right? So yp equal to your input x into m, and plus input x into m plus, and there is a c, mx plus c, and remaining. That means whatever the input we are feeding to your machine learning model, what your simple regression will do, that x value, that input value multiplied with the m and add to the c bias parameter, and that will give the predicted output. Those predicted output is nothing but the points on the line for the corresponding inputs. And finally, the line will be updated in such a way that the distance between the difference between the actual value and predicted value as small as possible. We're trying to minimize the difference or error between the predicted value, which are the points on the line, with the actual data points from the data set. Okay, so difference between these two is called as the error. So how we represent this error? So error can be represented as difference between my actual value and my predicted value. My actual value and my predicted value for all the samples. What are the samples are available in the data set, training data set? So all the difference should be, total difference should be as minimum as possible. So your learning algorithm will update model parameters in such a way that the difference between your actual value and the predicted value as minimum as possible. As minimum as possible. Okay. Now we have a small doubt. Like let's assume this is my X value. This is my actual output value. Let's assume this is my predicted value. Right? So for a particular X value, X1, my actual output is 4 and my predicted value equal to 3. For another input X2, my actual value is a 5, my predicted value is a 6. Then what is the error? What is the error here? So total error equal to, so difference between the actual value and predicted value, right? So actual value 4 minus 3, that's equal to 1, plus we have to sum it, right? We have to calculate the total error. That means my line should be minimum distance. Total distance from all the data points should be minimum. So plus 5 minus 6, that's equal to minus 1, that's equal to 0. Error equal to 0. Now it is showing that error equal to 0. But really error equal to 0? No. Here my actual value is 4, my predicted value is 3. Here my actual value is 5, my predicted value is 6. In the both cases, my mod is not predicting exact values, accurate values. There is some error. But here it is showing the total error equal to 0. Right? So how we can overcome this issue? So to overcome that issue, instead of using the only error, we are trying to take the square error. We are trying to take the square error. Hope you understand, right? We are trying to take the square error. So in order to avoid this type of the problem. So this is called as the square error. Okay. And if you see, if you take the only square error, if you have the thousands of samples, if you're adding the error for every sample, then what happened? The value becomes very, very large. It may throw an error right in the program. So to avoid that one, what I'm doing is I'm trying to do the small correction. That is, instead of taking the total square error, I'm taking the mean square error. Instead of taking the total square error, I'm trying to take the mean square error. So that's equal to E equal to 1 by, let's assume number of samples equal to N. Number of samples in the data set equal to N. That is the 1 by N in sigma actual value minus predicted value whole square. Actual value and minus predicted value whole square. Right? So this is the error. So now tell me, for any machine learning, for any learning algorithm, so what is the main goal here? What we are trying to do? We are trying to minimize this error. So during the learning process, the model parameters will be updated in such a way that my error should be minimized. So what is the error here? So my error equal to 1 by N sigma YA minus YP whole square. If the error coming to minimum, it is minimized, then definitely the value between these two will be minimized. That means your predicted value will closer to your actual value. Your predicted value is closer to your actual value. Right? So that is your main goal. For any learning algorithm or for any optimizer, we are using during the learning process, during the training process of a machine learning model. So its main goal is trying to update the model parameters in such a way that your model is predicting a value which is more closer to your actual value. When you are predicting value more closer to the actual value, then your error will be minimized. So that is the ultimate goal of your algorithm or of your optimizer. So that minimization of error is equal to 1 by N sigma YA minus YP whole square. And sometimes Instead of taking the mean square error, sometimes we can take the half mean square error also, 1/2n, half mean square error. So in case of instead of the mean square error, we can take the half mean square error also. Half mean square error also. Okay. So why I'm taking the half mean square error, I'm going to let you know later. So I'm taking the half mean square error here. Okay. So now see, from the machine learning concept to we are landing in the optimization problem. Why it is an optimization problem? Because we are trying to minimize the error. We are trying to minimize the error. So minimization of a particular object function. Here object function equal to this error. I'm trying to minimize this object function. Now we are comes to the optimization problem. I'm trying to integrate that optimization here. Even though we are studying about the machine learning, but we require that optimizer in order to minimize the error by updating the model parameters. So now tell me, so I'm trying to use the gradient descent algorithm for this case. I'm trying to use the gradient descent algorithm for this case. Okay. Now, I think it's clear, right? So any learning algorithm here, I'm trying to use the gradient descent algorithm. The gradient descent optimizer or gradient descent algorithm will trying to update the model parameters M and C in such a way that the predicted value YP is closer to my actual values, Like that M and C values or model parameter values will be updated. My ultimate goal is I'm trying to minimize this error function. I'm trying to minimize this cost function, or I'm trying to minimize this object function in such a way that in such a way the model parameters will be updated. So whatever the optimizer you are consider, that optimizer will try to update the model parameters in such a way that the difference between the actual value and predicted value will be close is minimum, or the actual value and the predicted value will be more close to each other. Like that will be model parameters will be updated. So what is our objective function now? What is our objective function? We are trying to minimize this error. Okay. So now the training process or learning process of a machine learning model, the main target is the minimization of error. So now we are trying to attempt this problem as an optimization problem. And I want to solve this problem using the gradient descent algorithm. Okay. Now I'm trying to explain further about this one. So finally, for a learning process or training process of a simple integration model. So what is its main goal? Main objective is minimize error. That's equal to 1/n sigma I equal to 1 to n y a minus yp whole square. Ya minus yp whole square, where actual value minus predicted value whole square. And further, we can write this error function as minimize error equal to 1/n, that is the number of samples, sigma I equal to 1 to n, ya, that is coming from the data set, actual values for a given input. What is the actual value? That's coming from the data set, and what your model is predicting. So please tell me, so what is the mathematical representation of a predicted value? How we can calculate the predicted value from the simple linear regression model? We discussed earlier also, previous screen, how we can find the YP or predicted value. This is the actual value. This is the known value, which is coming from the data set. N is called as the number of samples in the data set. And what is the YP? How we get the YP value? What is the mathematical representation of a predicted value, a predicted output for a simple integration? Because we are focusing on the simple integration model only. So what is the predicted value? Anyone, please? How we represent it mathematically, how we represent this predicted value? How we
Based
represent this
on
predicted
previous
value mathematically? Sir, YP equal to?
based on previous
M times X. plus C.
So YP value already we discussed, that is the YP equal to, so YP predicted value from the simple negation model is nothing but the whatever the input we are giving to the model, that is multiplied with a model parameter M and add with a bias parameter C, the line equation. So just substitute that one here, then you have the mx minus c whole square. So x value is coming from the data set input, and ya value is coming from the data set corresponding output, and n is called number of samples that is also available in the data set. So what are the model parameters in this case? In this case, what are the model parameters? M and C. So M and C are called as the model parameters. So whatever optimization algorithm we are trying to apply, what optimization algorithm or what optimizer we are using here will update these model parameters M and C in such a way that, because your model parameters are M and C, such that your error will be minimized. Here and taking the half mean square error 1/2n. Error will be minimized. So now our main goal is trying to minimize this objective function. We are trying to minimize this error function. We are trying to minimize this cost function. So the minimization of a particular objective function comes under the optimization problem. To solve this optimization problem, I am using the gradient descent algorithm. So in this objective function, what are the variables? So try to understand in perspective of optimization. So in this error function or in this objective function, in this optimization problem, what are the decision variables? What are the decision variables? Decision variables means the variables which you are going to calculate.
Yeah.
Madam?
Are they M and C only?
Yes, madam. Yes, madam. So these M and C are called as the model parameters. In case of like if we talk like a machine learning things, we can call it the M and C as a model parameter. If you see this problem as an optimization problem, we call M and C as a decision variables. M and C as a decision variables. So these are called as the decision variables, and this is called as the objective function, and this is called as the total objective function. We are trying to minimize now. Minimize a nonlinear unconstrained optimization problem. So I'm going for the gradient descent algorithm now. So that's called as the first gradient descent algorithm that is used in the machine learning, that is called as the stochastic gradient descent algorithm. So this is the stochastic gradient descent algorithm. I'm trying to explain nothing but the variants of the gradient descent algorithm only. Just name is different with slight changes. Okay. So how it will work, and I want to explain in detail about the how stochastic gradient descent algorithm will help to update the model parameters of any machine learning model. Model parameters of any machine learning model. So I think most of you, someone who are following since yesterday's class, they are able to help me also. They are able to help me while writing the algorithm or step-by-step procedure. Definitely they are able to. So now, what may be, because you are aware of gradient descent algorithm. Now I want to write same gradient descent algorithm in order to minimize this error function by updating the model parameters M and C. That is what training process, right? That is what training process. So training process is nothing but the updating your decision variables or update your model parameters in such a way that your objective function or error function will be minimum. That's what in the optimization perspective, we are trying to identify, we are trying to calculate, we are trying to update decision variables in such a way that your objective function would be minimum. So your objective function, the cost function, the error function, it should be minimum. So you have to find the M and C, you have to calculate the M and C. It's like a gradient descent algorithm only. So now tell me, what may be the first step? Just we will trying to apply what we did till now in case of the multivariable gradient descent optimization algorithm. Here also stochastic gradient descent optimization algorithm. So what the first step? Anyone please, what may be the first step? We will write the code also. So what may be the first step?
We should initialize the parameters.
Right, sir. Very good, sir. So we need to initialize the parameters. So let's assume random initializing. What are the parameters here for me? What are the variables or parameters here? M and C. So I'm initializing
and
the
C.
M value as some 1 and C value as some -1. You can use random initialize some value. So next. So initialization is complete. Initialization of our model parameters or destiny variables are completed.
Zeta.
Yeah,
Mm.
we need to initialize the eta. So let's consider eta value equal to something like a 0.1, whatever, some eta I have considered. Next,
Iterations.
Epochs.
epochs.
Mm.
So epochs also
Mm.
initialize, let's assume some 1000 iterations, epochs. Next. So these things what we discussed in the earlier for a multivariable gradient descent algorithm like this. But in this case, same all are covered, and few more things we need to, few more information is required. What else?
And number of
Samples. Okay.
yeah, some data
So
data
now
number.
a number of samples in the data n,
Yeah.
and also we required actual output value in the
Actual
data set,
data. Yeah.
actual input value. That means we have to read the data also. We have to read the data. We need to read the data. That's it. So this is the first part. First step is, this is the things we have to read. All the data we have to read. The complete data set, complete training data set, or data set which is used to train the model, the data set which is used to update the model parameters, the data set which is used to make a machine learning model to learn, that data set should be read. Along with the number of samples, and initialize your model parameter, learning rate, and number of epochs. That's it. What may be second step? So actually, in case of the stochastic gradient descent algorithm, how it will work means, so actually in our data, we have the multiple samples. So in our data, we have the multiple samples, X and Y. We have the sample 1, we have the sample 2, we have the sample 3, sample 4, like this, like X1, X2, X3, X4, and corresponding Y1A, corresponding Y2A, and corresponding Y3A, and corresponding Y4A, like this. All right. So multiple samples are there. This data we are going to feed. Then in the stochastic gradient descent algorithm, how it will work means, in a stochastic gradient descent algorithm, it will take one sample at a time and update the model parameters. Later take the second sample and update the model parameter. Later take the third sample, update the model parameter. Later take the fourth sample, update the model parameter. Then one iteration is completed. That is one iteration completed. That's it. One iteration completed. Now move to the second iteration. Again, pass the first sample, update the model parameter. Second sample, update the model parameter. Third sample, update the model parameter. Fourth sample, update the model parameter. So this process will be repeated in case of the stochastic gradient descent algorithm. For every iteration, for every sample, the model parameters will be updated. We are passing the one sample at a time to update the model parameters, right? Now, so based on this, anyone can tell what may be the second step. Okay, so I will tell. First, second step is, let's assume we are in the first iteration. So step 3 is, if we are in the first iteration, we have to take the first sample. Okay, take the first sample, sample 1. So maybe sample 1 is X1, Y1. Let's assume Y1A. We are taking this sample X1 and Y1A from this data set. First sample from this data set. We are in the first iteration. I am taking the first sample. So X1 and Y1A I have taken. So now tell me what is the fourth step. My intention is to update the model parameters. Clearly, trying to understand my word. I'm trying to update the model parameters. Using the stochastic gradient descent algorithm. It is a variant. Stochastic because I'm taking the sample by sample. I'm considering the sample by sample. Okay, I'm considering the sample by sample. Now tell me.
We have to take the derivative with respect to
Perfect,
m.
correct, perfect, Manik.
Yeah.
Now we need to calculate the gradient of our model parameter. What are the model parameters here? Gm and our model parameters are m and c. So calculate the derivative or gradient of our objective function or error function with respect to the model parameter m. So what is the gm value by seeing this one? And one more thing, because we are passing only one sample at a time. In case of the stochastic gradient, we are passing only one sample at a time. If you are passing the only one sample at a time, what will be the error now? So minimize error equal to, we are passing only one sample at a time, not 4, 5 samples at a time and calculating the error. Not. We are passing one sample and update the model parameter. That means we have to pass the sample 1, calculate the error, update the model parameter. So that error will be 1 by n equal to 1 only now. 1 by 2 ya minus mx minus c whole square. This is my error function in case of the stochastic gradient descent optimization thing. With one sample passing at a time. With one sample passing at a time. Right? So this is why I am taking n equal to 1, because I am not passing all 4 samples at a time. If I pass all 4 samples at a time, then I have to consider the n equal to 4. Right? I hope understand. I equal to 1 error plus I equal to 2 error, I equal to 3 error, I equal to 4 error. Sample 1 error, sample 2 error, sample 3 error, sample 4 error, add all, divided by 4, then we will get the mean value. But here I am passing only one sample at a time. So you have the only one here, then 1 by 2 ya minus mx minus c whole square. Now tell me what is the gradient? GM value.
It will be
So this is
minus
the
m.
GM is nothing but the dou E by
Minus
dou M.
yeah.
That's equal to 2 comes forward. 2 will be cancelled. 2 will be cancelled. Then I
minus
have the ya minus mx minus c. Okay. And we are differentiating with respect to m. So m coefficient is minus x. So minus x. So this is the GM value. Similarly, what about the gradient? Because in the previous, just before, when I am writing the code for the multivariable, I am calculating the gradient with respect to the x. I am calculating the gradient with respect to y in the earlier problem, 5x square plus 6y square plus 10. Here also with the two variables, m and c, we have to differentiate with respect to m, and we are going to differentiate with respect to c. We have to calculate the gradient with respect to m, and we are going to calculate the gradient with respect to c. So what may be the GC value? What will be the GC value? Dou E by dou C. That's equal to, this 2 comes forward, 2 will be cancelled. Then ya minus mx minus c, and the c coefficient is minus 1. So this is a minus. Hope you understand, right? So we are calculating the gradient. So what next step? Step number 5.
delta.
Delta. Step 10. How much change you have to incorporate for the model parameter m and c. So maybe you can write it as a del m, delta m. How we calculate the delta m value?
Minus zeta.
Minus eta and gm. That means here already we have the minus, here we have the minus, then we have the eta into ya minus mx minus c into x. Right? And similarly, del c equal to minus eta into gc, that's equal to eta into minus minus plus, and gc equal to this complete part. So we have the ya minus mx minus c. We are getting the del m and del c. So after step 5, what next? Step 6. Anyone, please? Anyone, please. So after this algorithm, we will discuss about some hand
Later update.
calculations and later we go
Yeah.
to code. Madam,
Update M.
update the M and update the C value. So M
Yeah.
equal to M plus delta M and C equal to C plus delta C. So what next? Now step 6 is over. Now what about the step 7? So step 7 will be, we are passing the sample 1. We are calculating the gradient. We are calculating the step length. We are updating the model parameter. Now we are going to go for the next sample. Sample equal to sample plus 1. We are going to the next sample. Next, what we have to do? Step number 8. Now we are checking whether if the current sample number is greater than number of samples or not. That means if I cover all the samples, then it goes to the greater than n. If I'm not covering all the samples in a data set, then it will be less than or equal to less than n. So if this condition is satisfied, which step we have to go? If it is not satisfied, which step we have to go? Let us assume if after updating the sample number, if the sample number is greater than number of samples in the data set, then what we will do? Okay, forget about this one. If this condition fails, that means your sample number is less than the number of samples available in the data set, then where to go?
Back and continue the same.
So we have the different steps. Step number 3, 4, 5, 6, 7, 8. So from this else condition is going, then from here we are going to which step number?
Step number 4, I think.
4. We have to go to the step number 4. If the condition is satisfied, then we are going to the next step. So what is the next step? Step number 9. Here, what we are going to do? Step number 9. So step number 9 is nothing but the samples are updated. So let us assume because if it's satisfied, that means all samples are covered. If all the samples are covered, what we have to do? See, all the samples are covered, then what we will do? We are going to the second iteration. All the samples are covered. Then we go to the second iteration, again start from the first sample. So what we have to do? Step number 9. So iter equal to iter plus 1. So what is the step 10? What may be the step 10?
Final value of M, I think.
Madam?
Final value of M will get.
No, madam. Here we have to check one more convergence criteria. That is, if the current iteration number greater than max number of epochs that you initialized earlier or not. If it is satisfied, yes, your current iteration number is greater than what max number of iterations we initialized earlier, then we are go to the next step. That means it's converged. So we are coming to the convergence part. If it is not, that means your current iteration is not more than the max number of epochs we initialized. Then where to go? Which step we have to go? So I am showing here the steps.
Number 1. Step number 3.
Yes, madam. We are going to the step number 3. Again, we have start from the first sample. So again, we start from the first sample. So go to step number 3. So here, next step, I said it the next step. So what's the next step? What to tell again earlier, step number 11. That means final values of M and C. Like earlier, we are printing so these are the final model parameter values. After taking the data, after running the algorithm for the 1000 epochs, what are the final M and C values? So those values are called as the final updated model parameters. Now, using these two updated model parameters, my simple integration model will able to predict the next hour load based on the yesterday's load when I see the new data. So this is the final updated M and C values. Now, using these M and C values, I will build an application. The application, if I give the yesterday 3 o'clock data, it will give the today's 3 o'clock data. If I give the yesterday's 4 o'clock data, it will predict the what is the today's 4 o'clock data. So based on these model parameters behind the application. So updating, so learning of a machine learning model, training of a machine learning model is nothing but the updating the model parameters in such a way that the error will be minimum, or the difference between the actual value, predicted value will be minimum. So to minimize that error while updating the model parameter, we are using the different optimizers. And in today's class, we discussed about the stochastic gradient descent optimizer. So this is the stochastic gradient descent optimizer. So I think you understand how a stochastic gradient descent optimizer will help the machine learning model to update its model parameters based on the available historical data. So data is used, I am using the data, I am using the algorithm, and I am using the model as well. So all three parts combining. If my child want to learn something, my child is required like a model, and ABCD alphabets are required like a data, and some approach is required like an algorithm what we discussed. So like that, model parameter will be updated. So model training or training process of a model, learning process of a model, any model is nothing but the updating the model parameters based on the optimizer what we are using. So updating the model parameter in such a way that your model is able to predict the output value more, not exact. I'm not able to give the exact, more closer to the actual output values such that that error will be minimized. So because even with the machine learning, our goal is minimizing the error. That means it's the optimization problem. To solve this optimization problem, I am using the gradient descent algorithm. So for the gradient descent algorithm, these are the steps yesterday we discussed. So I understood that you clear with this complete step-by-step procedure. Okay.
Yes, sir. Yes. Okay.
Sir, okay, na, sir?
Okay, sir. Okay.
Thank you very much, sir. So now
We
we
can
will
do
take
this same thing with nested loops also, right?
madam. Yes, madam. Now we will
Yeah.
write the code in the post-break session.
Yeah.
We will write a code and we will see how this parameters will be updated, and we will see whether we are able to get the predicted value closer to the actual values or not. Also, we will see from this simple integration model for one input and one output. Actually, in the Python, we have the multiple machine learning libraries. With that libraries, we can train and we can test the model with a single two, 3 lines of code. But in the backend, it will be happening like this. So we are trying to write the code from the scratch, not using the libraries for the training purpose. So anyhow, so now it is a 3:20. We will take a break for 10 minutes, and please join back by 3:30. So 3:30 for 15 minutes. I'm trying to explain the same algorithm with a numerical calculation. So after that, I'm trying to explain the code in Python. So please take a break for the 10 minutes.
Okay, sir.
Now we will work on some sample calculations. Later, we will try to write the program. We will try to write the program. Okay. Somewhere. Right. Modules. Yeah. Just I'm trying to take a small sample data. So
ఏం చేస్తాం ఫోన్లో మాట్లాడాలి.
yeah. let's consider this example. So let's consider a simple sample data set that one input, this is the XIA, and one output YIA. So this is the input and corresponding output is this one. Okay, and develop the simple linear regression model. So because it's a hand calculation, one iteration by using the stochastic gradient descent optimizer. What the first we have to take the data set. So what the data set here? 0.2, 3.4, 0.4, 3.8. So now coming to our our whiteboard. So step by step we will work. So step 1. So we have to initialize m equal to 1, c equal to -1, and you can take eta whatever it may be, 0.9, 0.8, 0.1, whatever it may be. A number of epochs, because it's the AND calculations, I want to do the epochs for only one iteration. And what else? And we have to read the data. So what are the data we have? 0.2, I think 3.4, and 0.4, I think it's 3.8. So data. So these are the data, X and Y data are read. That's the step 1. Okay. And that's it. So what is the step 2? So step 2 is start your iteration. So there is the iteration 1. And what is the step 3? So step 3 is nothing but the sample. So what is your sample? Sample equal to 1. Okay. So please tell me what is the step 4? Please tell me what is the step 4. So if you participate some actively, then it will be interesting for me. So what will be step 4? Anyone please respond. What is the step 4?
We have to substitute the sample one parameters in the error function.
Step 4 is
In the
nothing
error
but the
function.
gradient calculation. So GM already we derived the expression for a stochastic gradient descent optimization method. So GM equal to minus Y minus MX minus C. Y means is the actual value. MX minus C into X. That means minus. So YA value. That means we are in the sample 1. Sample 1 means this one.
Yeah.
So minus YA actual value, that is 3.4
3.4
minus M value, we assume it as a 1, he says is a 1, and X value, that is the 0.2. This is the X, this is the Y. Input and output. Minus C value minus 1, so minus into minus it will become +1, and multiplied by what is the X value? Again, it is a 0.2. 0.2. So we got some gradient value. We got some gradient value. We got gradient value. Similarly, we have to calculate the gradient with respect to the model parameter C. That is the minus YA minus M into MX minus C. That's it. That is the minus 3.4 Y minus M value is 1 and X value is a 0.2. C value is the -1, so it becomes a +1. So that's it. So we will get GC value here. We will get GC value here. So generally, I think we do the calculations also. No. Yeah. So you can see, I think gradient calculation. So we have 0.84. Here writing 3.4 minus 0.8. Yeah, here it is a 3.4. This is the 1 minus 0.2. 1 minus 0.2 means 0.8. 0.8 plus 3.4. 3.4 plus 0.8 into 0.2. That is the minus 0.84. We are getting here minus 0.84. And here what we have? In case of the dou E by dou C, we have the minus 4.2 value. So what is the step 5? So anyone please, what will be the step 5? So step 4 completed. So
Delta
what will be the
delta
step
M.
5?
Yeah.
So need to calculate the delta M. So delta M equal to minus eta. So 0.1, sorry, whatever it may be, 0.1. Easy calculation, I will took the 0.1. And what else? Delta GM
GM.
value. That is
Yeah.
a minus 0.84, I think. So it value equal to 0.084. And similarly, delta C equal to minus eta into GC. That is a minus 4.2. So that's equal to 0.42, I think so. This is the delta M and delta C. So next step 6. So step number 6 means what we have to do? We are going to update the model parameter. That is M equal to M plus delta M. That's equal to, so what is the M value? Initial M value equal to 1 and delta M
Yeah.
value equal to 0.84. So plus 0.084. I have the 1.084. Initially M value is 1. Now my M value is 1.084. Similarly, you can update the C also. C equal to C plus delta C, and the C value equal to, we initialize C equal to minus 1 initially, plus delta C value is 0.42. Now we have the minus 0.58. Okay, so what next? We are going to step number 7. So what is the step 7? So what is the step 7?
Sample number.
So step 7, see, gradient calculation, updation, for gradient calculation, changing the variable value, updating the variables, these 3 steps are completed for one sample. Now we are going
Yeah.
to the next sample. We have to
Next
update the
sample.
sample number. So sample equal to sample plus 1, that's equal to 1 plus 1, that's equal to 2. Right? That's equal to 2. Now we have to go to the second sample. We will see next step number 8. Step number 8 is the checking for the samples. If current sample number is greater than number of samples or not. So that means if current sample is 2 is greater than number of samples in our data set, 2 only.
2.
2 only. 2. So if it is satisfied, where to go? If it is not satisfied, where to go? We already discussed it. It is not satisfied. That means else condition. In else condition, we have to go to the, I think madam told. So we are going back to the gradient calculation, step number 4. Again, go to step number 4. So in the step number 4, what we have to do? Again, calculate the gradient GM equal to, so minus Y value. We are in the second sample. So GM equal to minus YA, actual value. Actual value is 3.8 because we are in the second sample. And X value is 0.4. So you can go minus Y 3.8 minus M value. We have to take the updated value. We have to take the updated value 1.084. 1.084 multiplied by 1.084 multiplied by, okay, Y minus MX. X value is 0.4. See, the second sample. In the second sample, X value equal to 0.4, Y value equal to 3.8. So Y value equal to 3.8, X value equal to 0.4. Plus, and whatever the C value, 0.58. Already we have the minus here, and here minus, it will become plus, and the 0.58 multiplied by X value, that is the 0.4. You got some GM value. Similarly, GC value equal to minus 3.8 minus 1.084 into X value 0.4 plus 0.58. We got some GC value. Now step number 4 is over. Now step number 5 again. We have to calculate the delta M. We need to calculate the delta C. How we calculate the delta M? Minus eta 0.1 and the GM value, whatever we have here, whatever the value we are getting here, that is the GM value. We have to substitute here. I think that also we calculated 1.84, 0.58. Yeah, this one. Okay. So this value, GM value, does mean dou E by dou M value equal to minus 1.58, minus 1.58, and dou E by dou C, gradient with respect to C, that's equal to minus 3.94, minus 3.94. This is the plus 1.58. Oh, it's minus only. Maybe I think it's a mistake. We'll see here. Don't know exact, see, GM. GM. Maybe both are minus. So it may be a minus, this also may be minus. So we have to calculate actually. Yeah, here we have the minus, so we will get the minus here also. And how we calculate the delta M value now? Delta M equal to minus eta 0.1 into our gradient. That is the minus 1.58. And delta C equal to minus eta multiplied by minus GC value. Minus eta into dou E by dou M. Minus eta into dou E by dou C. That is the minus 3.94. So here we have the delta M value, delta C value as 0.158. And here we have the delta C value 0.394. Okay. Now go to the step number 6. Step number 6. Now update M equal to M plus delta M. So M value is already 1.084 plus 0.158. Delta M value. Similarly, update the C value. C equal to C plus delta C. That's equal to C value is, what about the C value? Previous C value 0.58. Minus 0.58. Minus 0.58 plus 0.394. So we have to get the new M and C values. So what next step? Step 4 completed, gradient calculation. Step 5 completed, change in values. Step 6 completed, updating the values. So what next? Step number 7. So what the step 7?
Next sample.
So we are moving to the next sample. So sample equal to sample plus 1. Now step number 8, checking whether all samples are covered or not. If sample number is greater than number of samples or not, we will check here. Current sample is
2.
previously, see where this or the sample value 2.
2.
Now here sample plus 1, 2 plus 1, that's equal to 3. So now current sample value is a 3. Number of samples in our data set?
2.
Number of samples in our data set only 2. So only 2. Now this condition is satisfied. True. If it is a true, where to go? We already discussed it. We move to the next step. Okay. So what next step? Step number 9. If you try to remember, the step number 9 is updating the iteration. So iter equal to iter plus 1. That means already in which iteration we have started?
First.
Iteration number 1, first iteration. Now we are updating this one. 1 plus 1, that's equal to. Now what the next step? Step number 10. What we will do in the step number 10? Convergence. Whether our current iteration value is less than epochs or not. Whether true or false. If it is a true, we have to go to next step. If it is a false, we have to go to the, I think madam told, I think step number 3 earlier.
Yeah,
we are again start from the first sample. Step number 3. So again go to the step number 3. Now we have to check this one, whether we are going to the next step or going to the step number 3. So what is the current iteration? 1 plus 1, 2. But number of epochs, because it is a hand calculations, I am taking the number of epochs equal to only 1. So then what we will do? Number of epochs equal to 1. So this condition is satisfied. So move to the next step. So what is the next step? Step number 11. So step number 11 is just what are the updated M and C values? Use those M and C values to build your application. So see, deployment of a model is nothing but the using the updated model parameters. Using the updated model parameters while minimizing the error. So those model parameters we are using, deploying means. So I think you are clear with respect to the calculations part also. I think you are clear how stochastic gradient algorithm will work, and we are discussed with the numerical calculations also. Someone asking some question, please. Hello. So I think you are clear with respect to the what mean by the simple linear regression model, and what are the model parameters of the simple linear regression model, and how model parameters will be updated using the stochastic gradient descent optimizer. So here my main motto is I am trying to explain the stochastic gradient descent optimizer for the machine learning perspective. That's why I'm taking the one small, simple, basic machine learning model, that is a simple linear regression model, so that you are able to understand the optimizer well. If I take a complex model, it is very difficult to me to explain, and also it is difficult to you to understand. So that's why I'm taking with a small example. Same thing will be happening for the larger models also. but the number of lines of code required, the things may be somewhat complex. It's very difficult to visualize all the things. It is difficult to write the calculations also. Let's take the small example. Now we will work on the coding part. Okay. Now we will work on the coding part. So please, so I'm trying to use the MATLAB. Okay, first I will explain MATLAB. So I'm trying to save this file as something like SL or simple integration model with stochastic gradient descent optimization. Okay, so I'm starting with CLC and again clear all. Right, so please someone help me. What are the steps I have to follow next? So I'm trying to work on this same problem. So I'm trying to build a machine learning model. I'm trying to build a machine learning model. This is my data set. I'm trying to build a simple regression model to predict the output variable y based on the input x. And this is my input and output data. Okay. Now tell me what are the steps I have to follow. Suppose someone really listening what I'm saying, so are able to give the step-by-step process also, because it's not anything new. Because what to discuss earlier, I'm trying to apply same thing. So what will be the first step?
Do we have to import libraries here?
And
No.
here it is a MATLAB, madam. I'm trying to use the MATLAB. So no need to import
No
any
need.
library. We are writing from the scratch.
Okay.
In Python, we required some libraries.
Mhm. So initialization now we'll have
Yeah.
to do.
So first we have to read the, now we have to read the data first. So data equal to, so we have 0.2 and 3.4, and another is 0.4 and 3.8. Okay. So data next, we need to initialize M and C values. Just I'm considering M equal to some 1, and you can use the random initialization also. You can choose the random initialization also. So M equal to like define the lower value, like I want to -1 and upper value as +1. Okay, and now I want to initialize M equal to lower value plus rand multiplied by upper value minus lower value, and C equal to lower value plus rand multiplied by upper value minus lower value. Right? So M and C initialized, model parameters are initialized, and we have to choose eta equal to something 0.9. Any value some between 0 to 1 you can consider, and number of epochs equal to, maybe I can use some 100 or 1000 I'm considering. So what next? So all the initialization is completed here. I think so. Data initialization, M and C values, eta and epochs are completed. So anyone, please, what will be the next step? If you observe our
Number of samples, sir?
Sir.
Number of samples?
Yes, sir. Yes, sir. N equal to number of samples. How we got that number of samples information? So that is based on this matrix. So number of rows, how many rows are there? Those number of samples are there. Right? So if you observe here,
Yes.
you can take this line. Sorry. And come here and enter. So here we have the two samples. First sample consists 0.2 and 3.4, and the second sample consists 0.4 and 3.8. So we have the two samples, right? How we got that information? So we have a command called size in the MATLAB. size of, in which matrix we have the data? There is the data matrix. If you keep 1, it will give the number of rows. If you keep 2, it will give the number of columns. I want only number of rows. That will represent the number of samples. That's how we are reading the number of samples. So now, so what next? So if you observe our coding part,
Excuse me.
you can see there is a two loops are there actually. One loop for the iterations, outer loop for the iterations, inner loop for the samples, right? Outer loop
Yeah.
for the iterations and inner loop for the samples. Okay, so we need the two for loops here. So for iter equal to 1, 2, what I have to write? 1, 2 epochs. Max the number of iterations I have to run. And another for loop is, this is for sample. Sample equal to 1 to n number of samples. So close these two for loops. So inside this nested for loop, for nested loops, we have to write the code. So tell me, so what the next step now? We did calculations. We discussed about the algorithm. We did the calculations also. So next step is calculation of the gradient with respect to the m. So what is the value, GM value? We have the formula. Otherwise, I will go to that whiteboard. Here we have. So how we calculate the GM value? GM value equal to minus actual Y value minus M into X minus C into X. So now that's what I'm minus 1 into actual output. Where we have the actual output? What is the actual output here? What is the actual output here? What value should become here? Minus YA, actual value. For the first sample, what sample we are here? If it's sample equal to 1, first sample, sample equal to second sample, sample equal to 3, third sample, like that. So how we get that actual value of that corresponding sample? Actual output value of the corresponding sample.
Data first row, second
Right,
column.
madam. Data
Yeah.
first row. Why first row? Because it is the sample. Sample row. The first sample, first row. Second sample, second row. So data of sample, that is the first sample row. If sample 1 first row, sample 2 second row, whatever it may be. And which column we require? Second column.
Second column.
That is the data of sample comma 2. So if we have any doubt about this one, so just simply Control C. Let us assume if you are in the sample 1, then pass this one. Now we have the 3.4. First sample is the 3.4. Minus M value, M multiplied by, so X value. So what is the X value here? What is the X value? How we got the X value?
First
For the
column.
That is the first column.
First, yeah.
That is the first column. That is the first column. MX minus C.
How
from
do you
here.
check that in the command prompt?
Which one, madam?
Yeah, any expression, yeah.
Okay.
Yeah.
So what we are expecting here, the X value in the first sample.
Oh, you're
point.
just copy paste and you're executing.
Yes, madam. Yes,
Okay.
madam. Just I am
Yeah.
copy that part and paste it in the
Mm.
command window. I am verifying what it throw, what it will
Yeah.
give. So minus Y minus MX minus C into X value. So X value means this is only.
Yeah.
That's it. So this is what GM value. And how we calculate the GC value? GC value is almost same. See, you can observe here.
No multiplier.
So you could GC value, if you observe GC value, almost same as the GM, but no X in the last. So
So that X you explain once more, sir. X value.
sir, X value, sir.
So
So
data
actually,
of sample comma 2.
I will tell, sir. First of all, this the X is nothing but the input, na, sir. X is nothing but input and Y nothing but output, na,
Yes,
sir.
yes.
So
Yes,
input X means first column. You can see
yes,
the
yes.
data. You can see the data. This is the data, right?
Okay, okay.
The first column is X
Yes, yes.
and second column is a Y. So
Why?
I want the X here, right? So X means that sample, if the sample equal to 1, sample equal to 1, first row. Sample equal to 2, second row. But which column I want to extract from that row? First column, no, this is the X
First
and this is the
column,
Y.
yes.
So this is what we have
Okay,
to
okay,
extract.
okay.
That's why I kept the 1 here. Here I kept the 2
Okay,
because I want the Y here, Y minus MX. So that's why I'm
Okay,
taking the second column.
Okay, sir. Right.
So GM, GC is completed. So next thing is del M. Del M equal to, how we calculate the del M value? Minus eta multiplied by minus eta multiplied by GM,
GM.
gradient. And similarly, how we calculate the del C? Del C equal to minus eta multiplied by GC. Multiplied by GC, right? Right, that's it. Del M and del C. So once you calculate the change in step length for the M and C, now what we have to do?
Increment M.
So we are going to update the model parameters. M equal to M plus del M and C equal to C plus del C. Okay, M equal to M plus delta M and C equal to C plus delta C. That's it. So these are the steps we have to repeat and repeat for every sample and for every iteration. So already we close these ends. I hope you understand. So this far is closed, this far is closed. So this is our iterative process. So once it is coming out of the loop, when the algorithm is converged, then what we have to do? Just we can print if want. So printf. So M value equal to something percentage 0.2f comma C equal to percentage 0.f. So comma. So we have the M comma C values. That's it. So just save this code. So I think it's clear, right? So otherwise I will explain once again also. First we will run this code. So finally, what are the M and C values it is coming? M equal to 2 and C equal to 3. Actually, we started with M equal to some random value. We don't know. Randomly initialized. And C also random initialized. But at end of the 1000 epochs, I'm finally getting the M value equal to 2 and C value equal to 3. That is the updated model parameters of my simple linear regression model. Right? So once again, I will explain this piece of code. So no, don't bother about these two things. Now feed the data. Okay. And you can give the lower and upper boundary values from which range we want to choose that initial values of the M and C randomly. So now M and C initialization, random initialization, I'm using the rand function, it's the random initialization. And later I'm considering the learning rate eta. Sorry, learning rate eta and number of epochs and number of samples. Now, I think based on our previous AND calculations and based on our algorithm, we have the two nested loops. One for loop, outer for loop is the iteration and inner for loop for the sample. So inside these nested loops, we have to write the code. What we have to do? First, we have to calculate the gradient value with respect to the each model parameter. Later, calculate the change in the model parameter. Later, we are going to update the model parameter. So this thing will be repeated for all the samples for all the epochs. Once it's coming out of it, we have to store the values M and C. So that will be printed. So this is how the training or learning process of a machine learning model is happening. That's how model parameters are updated here. Then it's fine. Training is over. Actually, many things are in between. I'm hiding those things after this step. So some things we have to do. We have to use some test data. We have to calculate the errors. I don't want to go with all the things. Let's assume my model is perfectly trained. I'm assuming the training algorithm is completed. So I'm assuming that my model is perfectly trained and I'm getting the M value as a 2 and C value as a 3. Now, once the training goes over, let's assume I'm happy with the errors and my client also happy with the errors. What next I have to do? Training was completed. Let's assume I calculate the errors. Errors means with this updated model parameters M and C, I am giving all the input data. I am seeing the predicted output and I'm comparing the predicted output to the actual outputs. So I'm calculating the error and let's assume that errors are satisfied, not much larger. That's okay. I'm satisfied. Let's assume myself and my client also satisfied. Okay, I don't want to check all the things in between. Okay, that's why let's assume I'm satisfied with the errors. Then what we will do? Then what we will do? Then what we will do, please? Anyone, please? I'm unable to hear.
Can you repeat the question?
Madam, question is, so the training process was completed. I think you agree with that one.
Yeah,
And finally, we are getting the updated M and C values.
yeah.
So with those M and C values, that means my model was trained. That means my child human brain is updated for learning the ABCD. Okay, that means model was updated. Now, I gave the training data again to my model. Let's assume it is giving perfectly output. Same outputs, that means nearly close outputs are giving and errors are very small values. So I'm satisfied with those errors and my client who gave the project to me, he is also satisfied with that errors. Okay, no problem. That small error is not a big issue for us. He also accepted. So now what I can do? What next step?
For any other X, we can predict a Y.
Right,
from
madam.
that model.
So once we are
Yeah.
satisfied, everything happy with the training process and testing process, now we are going to deploy our model as an application. Now I am trying to build small application. So small application. Small application I'm trying to build. So actually application is what it will do. So here my focus, my problem is, so they have to give some values of X. So my model able to predict the Y. Output variable value it's able to predict. So my application also didn't like that. So my application will expect some input from the user and it will process backend based on the updated weights of a machine learning model that is called deployment and it will give the output. Now, when we are deploying a model into the application, so deploying of a model means what it means? Anyone please? What mean by the deploying of a model? Under the backend of the application, deploying of a model means? What
You are
mean
giving
by
the new values.
deploy
giving a
model?
new
What mean by
value.
deploy model? Madam, you are saying something?
Yeah, a deploying model would mean that you get the input from the customer or whoever.
No.
And gives the
Deploy model
prediction.
means, so deploy model, that already trained model is there, madam. In the previously we trained the model. We trained this model,
Yeah.
right? Machine learning model.
So already
Simple irrigation model.
the present.
Sir?
Okay, sir, you continue.
So actually, here we are trained the model, right? Simple irrigation model we are trained and we are updated the M and C values. And finally, we are getting the M and C values. Okay. Now I want to, that if the training is over, don't think that our task is completed. Our task is we have to deploy this model as an end user application. Some third party have to use that model. So we have to deploy in an application. So deploy in application is what it means. Deploy your model in an application is what it means. What we are keeping there.
Keeping the updated values
Right,
to
sir.
update.
Right, sir. That's it. So updating deploying a model is nothing but just keeping the updated model parameters in the back end of your application. So our updated model parameters are m equal to 2 and c equal to 3. That's it. But here we are able to see the model parameter. But if it is a big deep learning or machine learning, very big model, that we are unable to see those values. Just we are deploy it as a black box backend. It contains all the model parameter values, updated model parameter values, but we are unable to see at that time. But it's a very simple case. To make you understand, I am taking these steps. So deploying of model is nothing but simply deploying the model parameters and its architecture. Done. So if MN2 was updated, so what next? Now I am trying to build an application. What my application is expecting? My application will expect some input value X from the user, and the application will give the predicted output value. Let's assume like X equal to input, that's the command. It will give enter load data. Just example, let's assume my application want to predict the load for the next hour. Enter load data 24-hour back load data. Let us assume that means I'm trying to predict the load at 5 o'clock. I have to give the 24 hours. That means at least yesterday's 5 o'clock load. I have to provide that as an input. Once we got the input, how we got the prediction from your machine learning model? From our machine learning model, how we get the prediction?
Y equal to mx plus c.
Right, madam. That's it. So y equal to, that's the predicted output. Y equal to m multiplied by x plus c. That's it. Now, once it is over, then we are going to print it on the front screen. That's only required. What user expecting, he enters some value, operator will enter some value, and you want to see the output. What will be the next hour load? So you can print that one. Fprintf. So what's called what's the next hour load? Let us assume next hour load. Next hour load is equal to percentage something correct 0.2 f comma. So what's the value you have to print? Prediction. That is the y value you have to print. That's it. That's it. Now, so it's like application. You don't bother about the machine learning training and everything. The training is over, everything is over. Just we are deploying that model in an application. And deploying the model is nothing but, I said earlier, deploying of a model is nothing but uploading the model parameters, and also what else? Only uploading the model parameters is sufficient. Model deployment means it is uploading of the only model parameters.
No, we have to also give the new equation.
Right. That is the architecture. That architecture also we have to go. Our architecture equal to how? What is our architecture here? So go back here. You can see our architecture of a simple linear regression model here. We have to feed the model parameters, and also our architecture we have to feed. This is the architecture, right? Or the architecture model parameters we have to deploy, upload into the application, and architecture m into x plus c. That architecture also we have to define in the application. Both we have to upload in the application. So then you can run this one. Right? So what's asking? So enter the load data 24 hours back. Let us assume. So if I'm expecting 0.2, I'm giving 3.4. See, actually our data also you can check. If it is a 0.2, it should be 3.4. So I'm entering the 0.2 and my model is predicting the 3.4. And if you want to run the application one more time, you can run again. So you can, if you want to clear the screen, you can clear the screen. So run here. Sorry, already asking 0.2. It is asking enter the load data. Let us enter the 0.4. Just example. Just enter the 0.4. Then what is going? 3.8. So you can see the data also. If it is the 0.4, it should be 3.8. We're giving the 3.8. Okay, like that, the training process is happening and how the deployment is happening in case of the machine learning. So hope it's clear, right? This is a complete code for this one.
Sir, excuse me,
Ma'am.
sir.
Madam, please.
Sir, actually, I had one doubt.
Madam, hello.
Hello.
Please.
Sir, actually, we have kept negative sign before eta, na, sir, in delta M.
Okay. I need to send, right, madam?
Yeah, that's the doubt. Why just
Actually, yesterday we discussed, madam, that part. Okay, no problem. I will explain here. Why we kept the negative sign in front of the eta while calculating the step length. That's the question. So you can see here somewhere, yeah, here. Madam, anyone able to give the answer for madam's question?
Yeah,
Someone,
actually, if the random number, that random place that we choose for x is positive, then we have to decrease that to come towards the 0. So if we are positive, then we have to take a negative delta, and that's why that addition is done as minus zeta
Right,
times.
madam, question who are asking that question. So madam gave the right answer. That's it. So here the thing is, I want to explain once again that gradient descent algorithm. So let's assume this is my objective
Sir,
function
is
or
that
error
about
function.
error?
Madam,
Is that about error?
hello, madam. Once again, madam, please. I'm unable to hear. Please.
Sir, is this about error?
This is about the error function, madam, or objective function, what we are going to minimize. We are trying to minimize this error function. I want to reach the minimum error point. Okay. So we are assuming the model parameter or variable randomly something. Randomly we are taking some value as m equal to 1 or m equal to -1, something we are randomly chosen. Okay. But my optimal solution or minimum error point will be here, right? At this point, the slope equal to 0. At this point, slope equal to 0. And here we have the positive slope, and here we have the negative slope. My ultimate goal is, if my point is in the positive slope, I have to reach toward the 0 slope. If my point is in the negative slope, I have to reach toward the 0. That is my intention actually. Then what we are doing is, if the slope is positive, we are trying to move this point toward the negative slope. Then definitely it will come toward the 0. It will not jump directly. It will slowly, it moves toward the negative and finally landed in the 0 point. If the slope is negative, because we are keeping the negative sign in front of eta, then what happened? Negative slope becomes positive. That means try to update toward the positive side. So then what happened? It will move like this, it will move like this, and finally landed in the optimal point. So the negative sign we are considered in front of the gradient, because in order to update the model parameter to move from the positive to negative or negative to positive slope side, so that we are getting the 0 slope point, so that it reach the 0 slope point. Madam, is it okay?
Yes,
No problem. If you have any doubt, please ask me. If it is clear,
Yes.
okay, or I will explain once again.
Yes, sir, it's clear.
So
Thank
that's the only reason, madam. If see, you can observe delta m equal to, I am writing minus eta gm, right? Minus eta gm. So forget about the eta for some time. Forget about this eta for some time. So what happened? Gm is a positive, I am keeping the negative. That means I have to move toward the negative slope side. If the Gm is a negative, negative and negative, it will become positive, so it moves toward the positive slope side. So if it is a positive toward the negative moving, if it is negative towards positive moving, then definitely it will reach this bottom point.
Yes.
And why it is eta? So this eta will decide how much step length, how much step length I have to consider. It will be updated. What step length the model parameter will be updated, that will be decided with the eta. That's how we are considered delta m equal to minus eta gm and delta c equal to minus eta gc.
Yes. Yes, sir, it's very
Okay,
clear.
madam.
Thank
Thank you. So now we discussed with respect to in MATLAB actually. Now I'm trying to, we have the 10 more minutes. I'm trying to explain the same code, same problem, but coding in the Python, Okay. So I'm trying to change, do the slight mod, not same problem, only I'm trying to change the data set. Okay, I'm trying to change the data set. So okay. File, new file, SLR, simple integration model with SGD demonstration in the class. Let us know. Its name .py because it is a Python code. Create. Okay. So actually, in case of the any machine learning project, we have a large data, not 2 or 3 samples. Okay. So generally, this data is available in the form of Excel data. If it's numerical, mostly data sets are available in the form of the Excel file as XN file. Okay. Now, see this SGD practice. Now I have a sample data. This is my sample data. So these are the X values and these are the Y values. I'm trying to predict the Y value based on the X value. The data is available in the form of an Excel file. Generally, that is available in the real time also. Okay. Now I am trying to use this data. Okay. So copy this data and paste in which folder I am writing the code. I am writing the code where I am writing the code somewhere. No, class. No, somewhere I have written GDA. Please, just a minute. SGD class. Role of optimization SGD practice. Okay. SGD practice. SGD practice only. In practice only. Yeah, this is the file. Yeah. So already see. So here I am writing my Python file. In the same folder, my data also available. This is my data. This is my data set. Okay, na? In the same file, it is available. Okay. So make sure that your code file and your data set should be in the same folder. Okay. Now see how I am writing the code. So first import all the libraries. In the Python, we have to import the libraries. So import
ఇది ఎప్పుడు
numpy
చేసినాము
as
సేమ్
NP
ఇప్పుడు ఈ అబ్బాయి చెప్పేది
and import
2004 లోనే చేసాం ఇంపోర్టింగ్ డేటాలు అవన్నీ ఇక ఇప్పుడు చెప్తున్నాను అప్పుడు
so import pandas as PD. So pandas library generally used for the data related aspects. For data things, we are using the pandas. Okay. So because we don't have a time, but anyhow, I will explain. And the next thing is import math as empty. Import math file as a math library as a empty. And what else we have to import? One more thing we have to import, that is import random to random initialize the values. So most of the, of course, many are required. As of now, I am importing these 4 libraries. So what next step? We have to initialize. So let's take eta equal to 0.9 and epochs equal to 1000. And what else eta? Random initialization. So m equal to random initialization of the modular parameter. How we random dot uniform in the range of -1 to 1, I am initializing some value for the m. And similarly, C also, random dot uniform minus 1 comma 1 in the range 10, m and C values. Okay, so what next, please, anyone?
Data we have to get.
Right, madam. We need to deal with the data. So you can take data, some data, whatever data is equal to. So what the data? How we can read the data? Data is available in the same file SLR SGD class py. Oi. Sorry, 1 minute, please. Okay, this is the file that I have. So data, how we can read the data? So data is available in a sample data Excel file. Sample data Excel file. So what I can write here, data equal to, how we read the data? PD, here pandas, I'm using this library PD dot read. If it is a CSV format, I have to use the CSV, but it is in the Excel format, though I have to use the read underscore Excel. And inside it, so you have to call this part. So
Copy path.
So here, so that file name you have to call. That file name we have to call. Okay, so that's how we are reading the data. Now I am trying to run this piece of code for some time, and I want to print the data also. I want to print the data, whether I am getting the data or not. I am trying to print it. Okay, now run this cell code. Yes, so I'm getting the data, right? So this is the data which is available in my Excel sheet, X and Y, 0.1, 0.62, 0.2, 0.64, 0.3, 0.66, like that. This is the data is available. The data extracted and stored in a variable called data. Sorry, stored in a variable called data. Okay, so what we are going to do next? What we are going to do next? So just I completed earlier sample. I don't want to discuss with all these errors as of now. I don't want to discuss with all these errors as of now. Okay. So what I'm trying to do is, this is the data chain. So now, actually, generally the while learning process, what we are doing, if we have the for every unit, I have some set of questions with me, and with few number of questions during the training process while teaching the students, those problems I will dictate in the classroom. And whereas I kept a separate a set of questions to give the questions to test the person during the classroom delivery for a particular topic. If I have a 10 types of questions, 10 questions for a particular topic, and maybe I will explain some 3 to 4 questions in the classroom, and 6 to 7 questions kept aside, so that those questions will be helpful for me to test the student. That means actual learning capability or of a student will be coming when how he is able to answer the question which is coming, which is not covered in the classroom, that's not dictated in the classroom. So here also, if you have the huge amount of data, and the machine learning also we're using the huge amount of data, so we have to split the data for the training purpose and also for the testing purpose. So we have to split the data for the training purpose and the testing purpose. So that's what I am trying to do here. So I am trying to see xtrain, that is the input in the training data, xtest input in the test data, ytrain is the output in the train data, ytest is the output y in the test data, train underscore test underscore split. It is the one of the method which is used to split the data for the training and testing. What you have to pass in your data, whatever the input dot x you have to for, because our variable is x. You can see our input is x and output is y. That's why I'm using the data.x and data.y. Why data.x and data.y? Because whatever the data I am reading from the Excel file, that was stored in the data. Okay. And data.x means the first column will be coming to picture. Data.y means the second column will be coming to picture. So this data, input data and output data split for the training purpose and the testing purpose. And now what about this test size? So test size is equal to the 0.1. That means 10% of whole data will be go to the testing and remaining 90% of data is going for the training. Generally, we have to give the more data for the training and less data kept for the testing purpose. That's why 0.1, that means 10% of data used for the testing and remaining 90% of data going to the training period. And we have to keep random state equal to some number. You can give any number, that's not a matter. You can give 1, 2, 3, whatever it may be. But what it will do is actually splitting of the data is done randomly. Splitting of the data is done randomly. Okay. So if you give this number, that will done randomly, but every time it will give the same set of x train, y train, x test, and y test. So I'm not giving this part. If I split this code, if you run this code, x train has some data, x test has some values, y train has some values, y test has some values. If I run again, it will give some other values in the x train, some other values in the x test, some other values in the y train, some other values in the y test. But I keep some value here like this. Whenever you are keeping that value there, every time you are getting the same set of values in the x train and x test and y train and y test, not changed again and again. That is the reason how we are using the train test split method. But anyhow, I don't want to, it looks like I'm going for a hurry. I want to stop here for today. And while coming tomorrow, I'm trying to explain the Python implementation, how we can write the code to apply the stochastic gradient descent optimization method to train the simple linear regression model, and also how we can deploy that one also we will discuss using Python. That we will do in the tomorrow session for the first 30 minutes. After that, we will move to the some other optimizer. Some other optimizer we will move. So I'm trying, I want to close this session for today. If you have any questions, please ask. And tomorrow I will start from that Python starting point. So Python implementation of this stochastic gradient descent algorithm with training process for a simple linear regression model. So if you have any questions, please. Otherwise,
Sir,
we
I
will,
have sent one mail to you. I have sent a mail to you, Kalpana here.
madam.
Kalpana here. I have sent a
Madam.
mail to you where I have
Okay, madam.
written a program. Yeah.
Okay, madam.
And it is giving an error in the function, that linear programming function,
Okay.
linprog. So if you can tell me what the syntax error, or whether I have to import some labs.
Okay,
Can
okay.
you do that offline? Can you just
Yes, madam.
look at
Definitely.
the mail and yeah.
Definitely, madam.
The second
I will.
assignment problem you had given yesterday, I had tried to solve that.
Good, okay, madam.
Right.
Okay, madam. I will check that one and I will let you know through the WhatsApp group.
Yeah. Okay, right.
If
Thank you,
anything,
sir.
please. If no
Excuse me,
question,
sir.
Pooja, madam, you want to ask something?
Sir, could you please share this code in this group WhatsApp group?
Madam?
Could you please share this code
Oh,
which you have
definitely, madam.
written?
Definitely, I will share. So MATLAB part completed, so that I will share that code. But Python we will discuss tomorrow, and I will share that also. So anything else, please? Otherwise, we will close the session for today and we will meet tomorrow.
Thank you,
Okay,
sir.
thank you. Thank you very much to all of you.